Okay, I'm gonna be simulating a mock interview of sorts. Yeah, I'll be simulating a mock interview. I'll give myself a timer of 25 minutes. Let's see if we can do this. Let me just set this up properly. Should I give myself nothing? So, usually when it says optional, then let me give myself nothing, because I have done a lot of tree questions now. I don't really need a class necessarily all the time either. Like, basically, I'm trying to like mock the fact that what if I'm given nothing for this question? So, given root for method, and since this is a class, I'm just gonna like, the class should be already given, because we don't necessarily need to make a class all the time. We can just kind of do a method. So that's the question. I'm gonna go through my own examples. Given root for method, return list of int, I think. Let's just confirm if that's correct. Yeah, list of int, root. Can I know that it's optional tree node? Yeah, I don't know. I have no idea. Why can't it just be tree node? Why does it have to be optional? Because it can be none, that's why. That's what I'm assuming. Alright, and then let's just bring everything back. Alright, so I think that should put me in a good place. Let's get started with this question. Okay, starting the timer now. Given the root of a binary tree, imagine yourself standing on the right side of it. Return the values of the nodes you can see ordered from top to bottom. Standing on the right side of it. Huh, okay, well, there's boilerplate code to deal with, so let's just write that out. Right side view, we need an instance of self because we're in a class. We need a root. Is this root, like, can it be none? If so, then LeetCode already has this, but typing import optional. Oh my god, I cannot type. And then optional tree node, and we gotta return a list of int. In terms of what tree node can be, we have class tree node, and then we want a definition, an initializer. We can do like root, or sorry, val is equal to 0 as default, left is equal to none as default, right is equal to none as default, and then we can do self.val is equal to val, self.left is equal to left, and self.right is equal to right. Alright, so that's the boilerplate code. Now let's go on and do some examples. So you're saying we have this tree, right? And does it have to be a balance, like a binary tree, or yeah, it's a binary tree, so at most 2 nodes. I'll just like do something like this. Maybe one more, just to make it a bit more random. Okay, so we're standing over here, Okay. Return the values of nodes you see from the top to the bottom. So this is the top. And we're just going down from here? Like, do we just start from here at the left side, then like breadth, like almost like breadth first search, where you kind of just go one level, second level, third level. Huh. Why is it important that we're from the right side? Is it because we have to like start from top here and then go right first and then we can go left? Like so this way? So at this point, I'd probably be asking the interviewer, hey, like, what do you exactly mean by going from the right? So let me just take a look at the leak code example here. So we're standing on the right side, so we don't even consider the left subtree? Is that what's going on? Interesting. Setting the right side of it. Return the values of nodes you can see from the order from top to bottom. Oh, okay. So there's like an imaginary wall of sorts right over here. And you can only really see this right side. So you'd get, I guess I didn't put values in here, but if this was 1, 2, 3, 4, you'd get that list. And then 5, 6, 7. I think that's okay, right? I don't think the values matter in a binary tree. So, but that's not important right now. So I guess clarifying questions to ask. Again, root can it be empty? Like, and if it can be, I guess that's a test case to check. Can be empty. If we're standing on the right side, what if no right subtree, right? I guess there isn't exactly an imaginary wall over here. There's an imaginary wall. Like you can only see the rightmost elements. If there's no right subtree, then you have to choose the rightmost kind of path, right? So that would be like, imagine we didn't have any of this, or sorry, didn't have any of this, right? Then we'd be able to see this and this. So it doesn't necessarily have to be in the right subtree. It can just be it has to be just be the rightmost. What if no right subtree? Okay, that's the good thing to consider. Any other test cases? Anything else to ask? Empty binary search tree. Is it balanced? What are the values in nodes? No, I don't think that really matters though. Yeah, those would be some of my clarifying questions. Let's see what it says in the constraints. Number of nodes in the trees in this range. So can be 0, okay. Yes. And the node values are from 100 to negative 100. All right. Now, I would also ask what the ideal time complexity is for this problem. Ideal time and space complexity, I guess. Sometimes the interviewers, I don't think they'll really answer that. They'll just kind of say start working on it. So I don't know what time complexity and space complexity I should be working towards, but let me just think of a solution. So I need some kind of way to only see the right subtrees. So there seems to be always check the right first, then go into the left. Or like as a human, of course I can just visualize this and see that I just need the right node, right node, just to make sure that I'm correct in my example. At each level, the rightmost. Okay, so for me, this I see a breadth first solution immediately. I know I'm thinking yeah, I've already kind of talked about how I do this by hand. Like I just like kind of do an arrow, and I just showed you right here. But yeah, breadth first search solution is what I'm thinking about, and going down by level, and level, and then seeing which node comes last on that level. That's the node that we want to check. That first search doesn't make sense really because you can go deep, but you don't necessarily have to go into the left one. So now, how do I actually write this out? Well, first of all, what does breadth first search, like if we do a breadth first search solution, what's the time complexity for that? I think it's vertices plus edges. Vertices being like a node, and then the edges being the children, right? So for example, for this node right here, that's the vertex, and these are the children down here. All right. And space complexity, I guess it's also vertices plus edges. I think that's also something to consider because we're going to be keeping a track of it in a queue, and worst case, it can be this, I believe. So now, in terms of like coding this up, we need some kind of a queue. Right? A queue to keep track do we need to keep track of the level that we're at? Not necessarily. We don't really need to know the height or like the maximum depth of the binary search tree. You just need to like know what's the element at the end on that level. If we have like a for loop, then we wouldn't need to keep track of it. Maybe a while loop, then maybe we do. Let me see what else is there. Yeah, not much else. A queue, we have to kind of go through the nodes, add the neighbors to the queue. I guess I haven't really actually shown how I would do it. So imagine we start from here. Do we need to keep track of visited? This is only like one direction though, so I don't think we need to worry about the whole visited kind of aspect because this isn't exactly a graph, and I don't think we have to worry about cycles and all that. So I don't think we need to worry about that. But the queue, right? We start off with one in the queue. Okay? We pop that out, process it. Technically, it should go into like visited, but I don't think we need to keep track of it. And then we add 2 and 3. What we do need to do at this stage, not visited, but we need to like add it to our results list because this is the rightmost element, right? And then from this portion right here, we know 3 is actually the one that should come up. So at this point, we can pop both of these. So at this point, there needs to be some kind of like a check. Which one is it? We just cross this out. Okay. And then we leave 3. And we actually process the neighbors in 3. We don't even need to process the neighbors of 2. Interesting. So at this point, we add 3 up here in the results list. And we process the neighbors of 3. Oh, I guess I labeled it incorrectly. So 5, cross that, and 2, cross that, and process 3. There we go. And then 3, there's just one child, right, at this level. So that's the only one that's going to be rightmost. So we just process that, put that up here. And then the only child of 3 is 4, so we just got to add 4. Yeah, I guess we can save some time maybe by only looking at the right child. Well, technically that's what we're doing. That's what we did in this stage right here. We looked at 5 and 2, and then we got rid of 5. All right, so that's good. I should get into the code because we're 12 minutes in, 13 minutes in actually. So we need some kind of a queue. Import collection from collections, import DQ. I'm pretty sure that's the, if this is incorrect, I'll search it up. That's usually permitted, I've noticed in interviews. Q, DQ. Do we need a DQ? Let's keep a DQ. Let's keep a DQ. Do we need an edge case for the root? Maybe. Let's do if root is none, return empty list. QDQ. Can we add like root in here? Q dot pop left. Node. I think it was like this. Node dot pop Q dot pop left. We're popping off 1. And then from 1, we want to, first of all, we need like some kind of a results array. And we're going to be returning this results array at the end. So we want to do result.append node.value. And then we want to look at the node neighbors. Sorry, not neighbors, the nodes left and right. What do we do with the node left and right? At each stage, you can only add at most 2, so we don't have to worry about this window being like super large, right? So we either add nodes left or right, and we can do something like if node the right does not equal to none, q.append node.right. I think this is just better syntax like that. Q.append node.left. Okay. We only need to add 1. And then we want to do this multiple times. So we want like while q. Okay. I remember there being a for loop in past implementations that I've done in breadth first search. I'm not sure. while q node q dot pop left res dot append if node right q dot append node left res append node dot value, and then we pop again. Node dot value. Yeah. Okay. Let me trace this out now. So we got the empty case. Q dq root. Okay. While q it's gonna have 1 in here already. We pop this, add it to our results array. And then we check if right exists. If it does, we see it does, then we append it. And that's all. That's all we do to our queue. Sorry for the messy handwriting there. Okay. While queue, and yes, queue has something in it, we process it, pop it out, put it in here, and then check for right. If there is right, oh, but hold on, if there's a right but not a left, so gotta just make sure that maybe not an else case, but maybe just a if no dot left like that. All right. So we have that. Pop that. Put it into here. We check if it has a right. Does. So does the right. And then we move on to the next iteration. Q is still not empty. We check 3. Pop that. Add to res. And then we check. Does it have a right subtree? It does. Down there, it does. And then we maybe I'll do something like that. Else if no dot left. Right? Because we don't want to. It's just unnecessary work to add like a none. I think at the very least. So then we process that again. 4 up here, we check the children's. It doesn't have a right. Okay. Then it checks else if no dot left, but it doesn't have a left, so it doesn't add anything to the queue. Alright. So now we come back up here, we check for Q, and Q is now empty. So now it should return the result. Alright, so let's see if this works. Oh, that's not good. I'm at 21 minutes. Huh. Hold on. Maybe I'll comment this out. Hold on, let me refresh the page. Let's see. Oh, oops, I'm not logged in. No wonder. Hold on, let me close this video and open it up again.